We're going to look at a classification of problems, kind of a family of problems called optimization problems in this segment. And those problems involve maximizing or minimizing some kind of variable. Now, we want to, for example, we want to maximize profit or minimize cost or minimize distance under certain constraints. And so those problems, as you can imagine, if we're looking for maximums and minimums, we're going to be taking derivative and such things. Well, it's important that we understand the big picture, the broad idea, the general idea, the concept involved in these kinds of problems, because these problems occupy a very wide variety, broad spectrum of kinds of things that can come at us. So we need to know the general idea. It's not like in the elementary grades when we learn one little task and we apply that task to the same kind of problem again and again and again. This is a general idea applied to a lot of different kinds of problems. You won't see the same kind of problem twice, but the concept will be the same, and that's what we need to grab hold of. All right, here we have an open box. That means the top is open. Square base, let's say. The surface area of the box is 108 square inches. And we'd like to know the box dimensions that will produce a maximum volume. A maximum volume. Now, as soon as it says maximum volume, we're trying to maximize volume. So we're going to create an equation, or function, involving volume. And that's going to be our primary function. All right, let's do that. Well, here's the idea. We have a box, open top now, square base, so the length and width are the same. And we just don't know the height. We don't know the value of x either. We don't know the height, but we want to maximize the volume. Now, volume we know of a rectangular solid is length times width times height. For our particular box, the length and width are the same. So x times x, or x squared times h. Now, this again is the primary function, and that's the first task in dealing with this kind of problem. We want to identify a primary function. Another idea that we're given here is the notion of surface area, and here's how we're going to use that. You see, our primary function involves two different variables, and we'd like to create a situation where where volume is written in terms of only one of these variables. And in order to do that, we need another equation of some kind that we can utilize in this volume equation. We can make a substitution. Here's how that works. Think about surface area now. Now, the surface area would be the front, the two sides, and the back, along with the bottom. We don't have to worry about the top because it's an open top box. Now, the bottom, the surface of the bottom is just a square, so x squared would be its area. And the area of all of the other sides would be length times width, or it would be x times h. So, for surface area, we're talking about x squared for the bottom, and then 4 of these sides, which are x times h. Now, we're told that surface area is 108, so we have a nice little equation here in terms of x and h. Now what we'd like to do is solve this for either x or h. It's fairly easy to solve for h. There's a single letter h here, so we can isolate it rather easily. Kick the x squared to the left side and divide on both sides by 4x, and we have this. Now, we're going to substitute this information back into the volume equation in just a minute. But at this point in the problem, it's pretty easy for us to write down or have some thoughts about the feasible domain. What are the realistic values for x in this problem? Well, let's see. We were told that x is the length and width of the bottom of a box. Well, it doesn't make sense for x to take on negative values, so x is going to be, at worst, 0. 0 is pretty impossible as well. But so let's say x is positive. All right, x is positive, but how big can it be? Well, let's see. We have a surface area of 108, so that means that the area of the bottom can be at most 108. It's even unrealistic for it to be that big, but that's certainly a constraint here. That the area of the bottom of the box can't be any more than 108. So that means x squared is less than or equal to 108. So I could say then that the feasible domain is that x is greater than or equal to 0, and that x squared is less than or equal to 108. X then is less than or equal to the square root of 108. Now this idea of feasible domain is not terribly important in this problem, but it may be important in other problems. And when we get to the importance of feasible domain, I'll talk to you about it. But I want to bring it up here because it is an aspect of this family of problems that needs to be addressed many, many times. Okay, so we have two equations, a primary equation or a primary function and sort of a secondary function here. So we're taking this information about h, we're taking this expression, and we're going to put it into this position in the volume equation or the volume function. And I've done that over here. All right, so here's our volume function. Replace h with the expression, and then we'll go through and massage a little bit and simplify. These x's cancel, leaving an x factor here. X times 108, 108x, x times minus x squared is minus x cubed. We're still dividing by 4 and dividing 4 into both parts of the numerator, we get this. Now we would like to maximize our volume, so we're going to take the derivative of the volume in terms of or with respect to x. So dv dx is this, and now we'd like to find the zero of this function. That is, we'll set the expression equal to 0 up here, and we'll solve for x. And let's see, kicking this term to this side, we get 3/4 x squared. Multiplying on both sides by 4, we get this. Dividing on both sides by 3, we get this. So x is plus or minus the square root of 36, and x is plus or minus 6. The negative value doesn't make any sense here, so 6 is our solution. And at the moment, maybe it's a candidate for a solution. We might want to, at least in some problems, verify that 6 is indeed a maximum. We can do that pretty easily, can't we? We can take v double prime. You see, take the second derivative of v, and in doing that, we would get this. And when x is 6, v double prime is negative 9. So v double prime is negative, and that makes 6 a maximum value, you see. All right, so now that we know that x is 6, so that means that the base is a 6 by 6 square. What about the height? We might want to know something about that. After all, we were asked to give dimensions of the figure. So we'll go back to our h equation, which was this, and replace x with 6, and then evaluate, and we find h to be 3. So the dimensions of the box then are 6 inches by 6 inches by 3 inches to give us a maximum volume. Here's a problem that involves minimizing a distance. It says, which points on the graph of y equals 4 minus x squared are closest to the point 0, 2? Here's the graph of 4 minus x squared, and here's the point 0, 2. Now we're looking for the spots on the graph that are nearest to 0, 2. So those positions would be, roughly, I'm thinking right in here, and maybe right about in here. All right, so we're looking for the coordinates of those points. And it may make some sense that our primary equation is one that has to do with distance. The distance between 2 points, well, the distance formula is this. D is the square root of a difference in x value squared plus a difference in y value squared. And to give it meaning for our problem, now notice that one of the points is the point 0, 2. So a difference in x values would be x minus 0, and a difference in y values would be y minus 2. So I have plugged those values in here. This is just x squared, and expanding here we get this. Now we'd like to take it a little step further. We need to replace this radicand, or make a replacement within the radicand, so that we're dealing with a single variable. And that's a key. It's going to be a key to all of the problems that we talk about maximizing and minimizing. We end up with some kind of, usually, with some kind of primary function, and then that function involves more than one variable, so we have to make some kind of special replacement in order to get ourselves a function in one variable. Okay, that replacement here is kind of built into the problem. We have values for y, or replacements for y, because we know, now slide up here, and you see we have y equals 4 minus x squared. So we'll replace the two y's with 4 minus x squared down here. This y becomes 4 minus x squared, that y becomes 4 minus x squared, and now we just need to clean up. Let's go over here and do that. Simplifying under the radical, we get this. Now the distance is the square root of that. We want to minimize the distance, so we want to minimize the radicand. And to make matters a little easier here, I'm just going to write this as our primary function. I'm just going to say, well, let's look at it this way, and just this expression as an f of x. Now that's a technique. That's one of the reasons that I chose this problem, is to show you that technique of replacement, just to make matters a little bit easier. So f of x is this expression, which is the radicand, and f prime of x then is this, and we want the 0 of our derivative, and so we factor. Let's see, the value of x that causes this factor to become 0 is 0 itself. And here, solving for x squared is 3 over 2, so x is plus or minus the square root of 3 over 2. Now we still have some work to do, though. We need to kind of verify whether or not we have maximums or minimums here. We would be led to suspect that if we look at the graph, certainly, but we want to verify that using the techniques that we've talked about before. Also, we need to go through the process of finding the coordinates of the points that are on the graph. All right, let's begin by finding the second derivative. F double prime then is this. And now remember that x took on values, the zeros of the derivative function were 0 and the square root of, plus or minus the square root of 3 over 2. F double prime of 0 is -6, which, and the important idea here is that it's negative. And if it's negative, it implies that the distance in terms of 0 is a relative maximum. Relative maximum. How can it be a relative maximum distance? Well, let's see. Let me show you here why that is the case. Now remember, the graph looks something like this. And I'm going to exaggerate just a little bit here. Now, the distance at the point 0, this distance, you see, is a relative maximum. And it's relative because this isn't the maximum distance between this point and all of the points on the graph. Certainly there are points down here, for example, and down here that are more distant than this one is. But it's a relative maximum because from this point, if we slide our thinking over here, that the distance from that point to the graph is getting closer, 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 and there's a spot where there's a closest point, and then it begins to get farther and farther away. And so in a certain interval, this is a relative maximum distance, and that's what our second derivative idea is showing us here. All right, f double prime of plus or minus the square root of 3 over 2, just popping that information back into the second derivative function, we find 12, and the important idea is that it's positive. If it's positive, then we have a minimum idea. So the distance in terms of this value for x, those give us our minimum values. Let's find out the y component for these values of x. Go back to the original function, and for x being plus or minus the square root of 3 over 2, pop that information in place of x and solve for y. We find y to be 2.5. So these are the coordinates then of the points that are closest to the point 0,2. Now, as I've gone through this discussion, it may have occurred to you that there's another way to approach the problem. And there is. We're using here the techniques that we have talked about in terms of derivative and so forth. But there's another way to attack this problem, and just to kind of be complete with the idea, I want to show you that technique. You see, it may have occurred to you that if we're looking for a minimum distance, then think about if we have a line here and a point that's not on the line. The minimum distance from the line and the point, between the point and the line, is a distance that is a perpendicular distance. You see, now, think about that in terms of what we have here. We have a situation where we've got a point here, and we want the shortest distance from the point to the graph. And if we think about the graph being composed of a whole lot of tangent lines, then we want that very special tangent line that is perpendicular to a line that's from this point to a spot on the graph. That is, you see, if we're thinking of a tangent line down here, then certainly the line that goes to that point would not be perpendicular to the tangent line. So this segment wouldn't be perpendicular to the tangent line. But if we find a spot where we do have this perpendicular idea, you see that we have this perpendicular idea, then that is the point where the point on the graph is closest to the point 0, 2. So using that idea, then think about the slope of this. Now this is the point 0, 2, and slope is difference in y's over difference in x's, so the slope then is y minus 2 over x minus 0. And the perpendicular slope is really what we're after here. You see, we don't want information about the slope of this little line. We want the slope of the tangent line. So we're talking about perpendicular slope, and we know that lines that are perpendicular have slope numbers that are negative reciprocals of each other. So we want the negative reciprocal of this, so it's the negative reciprocal of it. And now we go to our equation and its derivative. Now, what does derivative mean? Slope of the tangent line is at a point. You see, now we have slope of the tangent line at that point, you see, and we just make that replacement here and then just clean it up. Now, notice that in this form we have both x's and y's and a y value in our equation. Well, we have a nice replacement for y. It is 4 minus x squared, so replacing this y with 4 minus x squared gives us a way to solve this now for x. All we need to do is clean it up and simplify and so forth. I've done that up here. I've done a little cross multiplication. I've kicked the x to the right side, multiplied things out, collected. Now we're ready to factor. And once we factor, we get into this form, and the values of x that cause each of the factors to become 0 are these. So x is 0, or x is plus or minus the square root of 3 over 2, as we found using the other method. For this problem, suppose we have two posts in the ground. One of them is 12 feet high and the other is 28 feet high, and the two posts are 30 feet apart. We'd like to attach from the top of each post a wire and join the wires at a single stake somewhere in this region so that we minimize the length of the wire, the amount of wire that's used to tie these off. So the point might be right here where we have the wire, it could be over here where we have the wire, and so on. Now, in order for us to minimize that distance, let's say it's, roughly here, let's say. We're going to have a stake right here, so we'll have a wire coming in from the top of that post and from the top of this post. And this distance, let's just call this distance x. And if this is x and the whole distance is 30, then this distance is 30 minus x. And we need to represent these distances, and we'll call this distance y and this z. And now, our wire, w, will have a length that is y plus z. And we're trying to minimize w. Notice in this problem, first of all, before we get thick into this problem, that this is an equation that we came up with all by ourselves. Our primary function is one that we invented for the purpose of solving this problem. In other problems, they might come from formulas. But the idea is that in this section, you're noticing that we have a wide variety of functions to deal with. Every different problem will have a different kind of function. Well, I mentioned that before, but it's important to realize that you're looking for a primary function, and it may be something you haven't seen in other problems. But just be aware of that as you go through your problems for homework. All right, we're trying to minimize w. And another factor here, since this stake can be anywhere from this point to this point, the value of x could be 0, you see, if the stake is right there at the bottom of this post, or the value of x could be 30, or it could be any value between 0 and 30. So we might just put a little note here that 0 is less than or equal to x, and x is less than or equal to 30. X is between 0 and 30 and could be either of those ends. Okay, with that in mind, now let's represent y and z. You see, with our primary function now, we'd like to write this in terms of x, if we can possibly do that. Well, we can certainly do that. We have a couple of right triangles here, and we know that y here, y squared is 12 squared plus x squared. Z squared is this side squared plus that side squared, and all it is a matter of algebra. So let's see. We have for the left side little right triangle, y squared is x squared plus 12 squared, or y then is the square root of the sum of those two. And for the z distance, z squared is that binomial 30 minus x squared plus 28 squared. And z, therefore, is the square root of all of this expression, and I've cleaned it up a little bit. I've just expanded this multiplication and collected like terms to get this. Now we know that our wire is y plus z, and here's y and there's z, so w then is the sum of those two radicals. Gee, it's starting to get a little bit heavy with the algebra, isn't it? Well, no problem. We're going to take this w, and we want its derivative. So here's the w up here, and here's the derivative. Here's w prime. Now we're using the chain rule here. I'm going to walk through the algebra a little bit. I want to show you just enough of the algebra in order for you to be able to follow what's going on. But I don't want to belabor the situation and spend an awful lot of time with it. You might want to look over these problems from time to time to make sure you understand the algebra, but it's the overall concept that's even more important than that. What's the big picture? What's the whole idea of what we're trying to do here? That's what's important. All right, let's go through the algebra here. W prime is, now with this, I'm thinking of x squared plus 144 to the 1/2 power. And so by the chain rule, it's 1/2 times the radicand to an exponent, which is 1/2 minus 1, or negative 1/2, times the derivative of x squared plus 144. So that's 2x. And in a similar way over here, we have 1/2 times this to a power which is 1/2 minus 1, or negative 1/2, times the derivative of the radicand, which is 2x minus 60. All right, now the negative 1/2 just means we'll pump this expression down into the denominator and put a radical on it. So in the denominator we have the square root of that. Now notice the cancellation opportunity here. The 2 cancels with the 2 and the 60 over here. 2 just divides both parts of that binomial. So we have x minus 30 in the numerator and the square root of that expression in the denominator. Now back over here in a similar way, we have this 2 cancels with that 2, leaving x in the numerator. And in the denominator, we have the square root of the x squared plus 144. Now we're setting w prime equal to 0. We want to solve this for x. And now it's kind of an exercise in algebra at this point in the problem. Remember, the technique for solving equations involving radicals was to isolate the radical on one side and then square on both sides. Now, when you have two radicals involved, or radicals involved in more than one term, you separate the two radicals and then you square on both sides. Well, to separate these two radicals, I'll just take this term and kick it to the other side. So I have negative this term equals that term. And now I'll go about the squaring process. When I square, oh, I forgot to square the x. This x is squared, so that's x squared here. And when we square the radical, we get the radicand, and on the right, x minus 30 squared gives this trinomial. Squaring the radical, we get the radicand. And at this point, we cross multiply. Now, I've taken the liberty of going ahead and cross multiplying and simplifying a little bit because I don't think that's such an important kind of thing for us to go through every step with, but it's x squared times this, and then this binomial times that trinomial, and then lots of terms emerge and we collect the like terms and so forth. And once everything clears out of that, we get this trinomial. Now we want to, and it's set equal to 0, we want to factor this as if we can. It does have a common factor of 320. We snag that out and we get this, and this is factorable into these two factors. Now if we didn't see the factorization here into these two factors, remember you just pop this information into the quadratic formula, and we can resolve the situation rather easily like that. But at any rate, it is factorable. These are the factors, so the values of x that will cause each factor to become 0 are x equals 9 and x equals negative 45 over 2. Now the negative 45 over 2 doesn't make any sense because remember x is between 0 and 30 and could be 0, could be 30. So 9 is our primary target for an x value, but we need to check the situation here to see if the x could be 0 or 30. I mean, after all, if we tied made the stake right here, then we would have a situation where the wire would just go down this pole, you see, and then be connected here and then go all the way to the top of the other pole. And if x was 30, then it would slide it over here and we would have, you know, the wire going here and then straight up to the top of the pole. So we have to consider those situations in this problem. So let's do that. Let's consider the idea that x is 0. We start with the idea that w, the wire, is y plus z. Now if x is 0, what is w? Well, come back over here. I have something for it over here. But remember, if x is 0, then the x is clear over here under this post. And so the y distance is just the length of this pole. It's 12. And the z is, well, z squared is the square root, z squared is 30 squared plus 28 squared, or z is the square root of 30 squared plus 28 squared. And that's what I have over here. W is 12, that left side pole, plus the square root of 30 squared plus 28 squared, and simplifying we get approximately 53 feet. All right, now what happens if x is 30? Well, if x is 30, then our stake is at the bottom of the other pole, and we kind of have a symmetric situation. The stake is over here, so we're talking about, here's our y, and y squared is 12 squared plus 30 squared. Y then is the square root of 12 squared plus 30 squared, and the z value is just the length of this pole. So we have, let's see, if x is 30, then w is the square root of 30 squared plus 12 squared plus the length of the other pole, 28. And that's approximately 60 feet. Now, so far, the shorter wire happens when we're below that left side pole. All right, let's see what happens if x is 9. Now, when x is 9, we have the situation where, let's see, if x is 9, that means the stake is here, that's 9, and this is 30 minus 9, or 21. So it's pretty easy then for us to calculate the y and the z. The y is the square root of 12 squared plus 9 squared. Z is the square root of 21 squared plus 28 squared. So if x is 9, w would be the sum of these two radicals. And under this radical, we have 225. Under this radical, we'd get 1225, and those both happen to be squares. So w is 15 plus 35, or 50 feet. And that then is our shortest distance for the wire. So we know that that stake needs to be 9 feet from the left side pole. A wooden beam has a rectangular cross-section of height h and width w. The strength S of the beam is directly proportional to the width and the square of the height. What are the dimensions of the strongest beam that can be cut from a round log of diameter 24 inches? Notice in the problem we're trying to maximize the strength of this beam, and we're given a relationship between the height and width of the beam for maximum strength. Now when the problem says that S, the strength, is directly proportional to W and the square of H, it means that there exists a constant of proportionality K, such that S is equal to K times, now let's see, directly proportional to W, and that means times the square of H. So we have this. Now this is our primary function. This is the function we're trying to maximize. We're trying to maximize the value of s. And we need to use information about width and height from our diagram. Now remember, the diagram is something like this. We have a cross-section of a tree, and we know that the diameter here is 24, but we're cutting the beam out of this cross-section. And the diameter is thought to be here. We take it to be this diagonal distance. And that's really important because in doing it that way, we have a right triangle, and now we have a built-in relationship involving width and height. Okay, so we know then that the width squared plus the height squared is equal to 24 squared. Width squared plus height squared, 24 squared. And we can solve this then for either w or h. But in fact, it's easier if we think about it, if we look at what we have here. Notice we have h squared here. We can make the replacement for h squared instead of for h or instead of for w. Any way you look at it, though, it's okay. If we solve this for h squared, we would have, let's see, 24 squared is 576, and subtracting w squared on both sides, we get this. So h squared is replaced with this binomial. So now our function is this. And multiplying kw times each of these terms, we get s to be 576 kw minus kw cubed. And now we want to find the derivative, and the derivative is this. Now notice that k is a constant, and just treat it as though it were a constant because that's what it is. So we're thinking of a constant times w, and when we take the derivative in terms of w, we're left with just the constant. And here it's 3 times the coefficient, you see, so 3 times k, and then w squared. Okay, now we'd like to set this derivative function equal to 0 and solve it for w. Factoring out 3k, we get this, and then solving for w squared is 192, so w is the square root of 192. We know it's plus or minus the square root of 192, but it only makes sense for the positive value to be used here. Now, I didn't talk about any kinds of constraints or any kind of extreme values for w. I mean, after all, if we think about, come back over here to the diagram, if we think about squeezing this situation into an extreme situation, that is bringing w into a very thin value, making w approach 0, it just doesn't make sense that that beam would have any strength at all. So, you know, although w could theoretically be 0, and the longest that it could be is to, well, let's see, if we stretched it out here, it could be as long as 24 inches. But gosh, that just doesn't make any sense here. Incidentally, I put feet, that ought to be inches. Okay, so the extreme values don't make any sense, and this is the only one that does make some sense. Let's verify that this is indeed a maximum idea. We would think about s double prime, the second derivative of s is minus 6kw. And if we're using w as a positive value put in place of w would make this value negative. So when w is positive, that implies that the second derivative is negative, and that implies that we are looking at a maximum. Okay, now the approximate value of the square root of 192 is this. And we can sort of take our choice as to which one we want to use, but just understand that this is an approximation, and that's more of an exact value. Well, it was asking us for dimensions, and we have w, we need to find h. We can find h by using the equation that we derived earlier. That is, h squared is 576 minus w squared. W we found to be the square root of 192. Squaring, we get the radicand. 576 minus 192 is 384. So h then is the square root of 384. And that's approximately this amount. So the beam should be, now notice that I'm going to write the dimensions of the beam as an exact value here. This is w, and this is the h value in exact terms. If we want it in approximate terms, then we would use something rounded off from those decimals above, 13.9 inches by 19.6 inches, for example. A rectangle is bounded by the x and y axis and the graph of y equals 6 minus x over 2. What length and width should the rectangle have so that its area is a maximum? Well, it may seem a little confusion about this bounding business, but when we look at it on a graph, it's not too difficult. Here we have the x and y axis, and this line is the graph of y equals 6 minus x over 2. And if we take a point on the line, that point will help to define the sides of a rectangle. And then the rectangle has a particular area, and if we move that point along the line, we can see that the area of the rectangle changes. And all we want to do in the problem is maximize that area. We want to find the spot on the graph that maximizes the area. It's going to end up being in about this position, but let's calculate that position. We start with the area formula. Now, area is length times width, but in terms of the x and y axis here, the length is x and the width is y, so area is x times y. But the y used in the area formula is the same as this y. You see, it's just a vertical distance defined by this expression, so we can replace the y with 6 minus x over 2. And then we can clean up a little bit. This becomes 1/2 times 6x minus x squared. And now it's pretty easy to take the derivative. That's a dA over dx, and it's 1/2 times 6 minus 2x. Now the dA dx, we can express it this way. We can use this notation. That's just fine. It's the derivative of the area with respect to x, or we could just call it an a prime. I'm going to call it an a prime here for convenience. Okay, let's see. 1/2 times 6 minus 2x is 3 minus x, and we know that we have a maximum or a minimum in situations like this when we find the zero of the derivative. So the 0 for a prime means that we replace that a prime symbol with 0, and we solve for x. X turns out to be 3. Well, an x of 3 will give us the maximum area of our rectangle, but we need the y that corresponds with that x of 3, and it's pretty easy to find with our relationship here. Replace the x with 3, and we find y to be 1 1/2. So we can say then that the area is a maximum when x is 3 and y is 1 1/2.